Alright, in this last video for Module 2A, talking about biopotentials and where they originate, we want to discuss the EEG or electroencephalogram. So the EEG is what we measure when we look at the electromagnetic signal coming from the brain. Here is a cross section of the brain. This one has a center slice, so we're looking kind of from the center. This one we're looking from the edge of the scalp. Um, The front part of the brain is referred to as anterior, the back part is posterior. The top is superior and the bottom is inferior. And so that's one of the ways that we discuss the brain. The other is to talk about lobes. The temporal lobe is sort of the side lobe of the brain. It sits over the ear. The frontal lobe is the frontal portion of the brain wrapping around to about mid of the top of the scalp, at which point we have the parietal lobe that then runs probably 3/4 to 80% of the way along toward the back of the scalp, and then the occipital lobe uh, is the back part of the scalp. Sitting below the occipital lobe is the cerebellum, and it's generally considered a region of its own because the cerebellum is sort of like a pre-signal processing kind of thing in the brain. You can actually live without your cerebellum, but you tend to have then timing problems with how the brain signals the extremities and how it perceives things. So, so this is one point of view. The corpus callosum is a very important region of the brain. It connects the left hemisphere and the right hemisphere. The mid parts of the brain, the thalamus and the other regions, the hypothalamus, in the mid part of the brain, are what control the autonomic functions of the body. So, in other words, breathing, the heartbeat, the metabolic rate. And so, because they're so important, um, you can actually live without a large part of your of your of your brain, but this deep center part is key to maintaining body function. And so, for that reason, people believe that that's the reason that this portion of the brain is deep within the center of the brain. That way, if you do get a concussion or a brain injury, you're less likely for this midbrain, this middle of the brain region, to be affected. So there's some protection of that part of the brain. Um, Once again, some of these lecture notes are taken from the Wikipedia site on electroencephalography because I really like the way they summarize things. And then the rest of this lecture are taken from the notes or from the textbook, chapter 4. So the brain's electrical charge is maintained by billions of neurons. And these neurons are electrically charged or polarized by these membrane transport proteins that we saw earlier in the chapter. And they pump ions back and forth across the membrane. The neurons constantly exchange ions with the portion of the brain that's outside of the neuron in order to either maintain a resting state potential or to propagate an action potential. And so we have ions of similar charge that repel each other. When ions are pushed out of neurons at the same time, they push their neighbors, who push their neighbors, and so on. And this process is referred to as volume conduction. So neurons, while they do act independently, they also act in concert and as a group. The electric potential generated by an individual neuron is way too small to be picked up by an EEG or an MEG. And so when we measure the EEG, we're always measuring a sum of synchronous activity of thousands or millions of neurons that have a similar spatial orientation. Now, if they don't have a similar spatial orientation, their ions don't line up and create waves that we can detect. So pyramidal neurons in the cortex are thought to produce the most EEG signal because they're well aligned and they fire together. And because the voltage field's gradients falls off with the distance squared, activity from deep sources is much more difficult to detect than currents near the skull. So typically the rule of thumb is when we take a normal EEG, we figure maybe we can measure 1 to 1.5 inches below the surface of the scalp. Beyond that, the signal is going to have to be really strong, and the detection technique, signal to noise elimination, and even the way the experiment is set up would have to be very well managed. We can see if we can link to these pyramidal neurons. So as you can see, they are long, um, and these tend to be oriented radially. So in other words, they're perpendicular to the surface of the scalp, which makes their dipole field then perfect for us to be able to pick up with an EEG reading. So what then we're actually looking at when we're looking at an EEG is we're looking at potentials that are generated by probably thousands, if not millions, of neurons. These neurons act synchronously. What that means is they're firing in phase. And so if we, as you know, electromagnetic fields are linear, and the sum of a field due to an oscillating dipole, or a field due to multiple oscillating dipoles is just the vector sum of the field due to each dipole. So what you're really picking up with the EEG is a linear superposition of all of these dipoles. If they're firing synchronously, then you pick up a waveform that actually represents the synchronous activity of these groups of cells. Here is another sort of cartoon picture of a pyramidal cell. You can have excitatory or inhibitory inputs, and that then affects the type of the way the cell fires. But typically, when we measure an EEG wave, we're not thinking in terms of excitatory or inhibitory because we tend to be looking at statistical properties of the EEG wave activity. So when you measure an EEG, it looks something like this. It looks a lot like noise. So when you have current that flows to and from, um, that flows back and forth along these pyramidal neurons, you tend to get wave-like activity. These are modeled in the people who do modeling on this model these groups of neurons with synchronous activity as oscillating dipoles. So it's very much like modeling an antenna. So if you would visualize that your brain consists of your brain activity consists of multiple antennas emitting signal from various parts of the brain. This is the way the signal is received, and we will talk much more about this in one of the later chapters when we talk specifically about the EEG. Keep in mind, like EMG and ECG, one could devote an entire course to EEG and EEG analysis, and in fact, we will probably offer such a course next summer online, but one could devote quite a bit of time to that. So we're really just brushing the surface, and I particularly could talk about EEG a lot because that's my field of research. So what you see here is you see a typical cap where we have electrodes at very specific locations. These locations were sort of determined a number of years ago. As you notice, the reference is from 1958. It had to do with finding two key points. This point right here where the bone above the nose has its deepest indentation, and then if you feel the back of your head, you'll feel a little ridge on your scalp. And so from there, the complete distance is measured, and then one goes 10%, 20%, 20%, 20%, 20%, 20%, and 10%. Hence the name, the 10-20 electrode system. And the same is done if you look and you find the little bone right at the ear, and you go across the head from left to right, and you do the same 10, 20, 20, 20, 20, 10. And so that's where the coordinates for the electrodes are located. And then each one has a name, F corresponding to frontal, C corresponding to central, P corresponding to parietal, O corresponding to occipital, and T corresponding to temporal. So those are basically the lobes of the brain. Central is not considered a lobe because it runs right in the middle between the frontal, temporal, and parietal. But but basically that's how the original labeling was done. So what's happening is each one of these electrodes, and we'll discuss electrodes in a later lecture, but each one of these electrodes is basically picking up a signal from all of the surrounding synchronous neuron dipole activity. So let's suppose within your brain you have 5 or 6 of these brain regions that are producing these synchronously oscillating um, dipole electromagnetic waves. So if you have 5 or 6 of those, then each one of these sensors is picking up a superposition of those 5 or 6 oscillating dipoles. Now, the assumption is often made, and it's not a bad assumption at all, that, for example, sensors that are near the front of the head are going to be much more likely to pick up neuronal activity that's right here in the front of the head, and much less likely to pick up neuronal activity that's here in the back of the head. So often people will look at signals at the sensor level or the electrode level itself and make some connection between where the electrode is located and where the activity in the brain actually occurs. But it's important to keep in mind that that is an assumption because, for example, if I had very weak activity near the sensor and then very strong activity a slight distance away, those two activity levels might look roughly the same at my sensor location. So amplitude figures in as well as the physical extent of the oscillating dipole and the number of neurons involved and the strength of the signal. So all of that figures in. So it's actually a very difficult problem to figure out where the signal is coming from, especially the fewer the sensors you have, the more difficult it is to know that. So here's some examples of what EEG activity is. It's first important to say that conventionally EEG activity is divided into frequency bands, and these 4 here at the top are the respective frequency bands, with delta being the lowest frequency, and you can see here's 1 second. So delta frequency ranges from 0 to 4 hertz, theta from 4 to 8, beta from 8 to 12, and alpha from 12 to about 25, depending on who's making the definition. That upper limit ranges from 24 to 30, depending on the reference that you're actually looking at. But those are I'm sorry, that's beta. So he's got alpha and beta flipped. Beta is the higher frequency, alpha is the lower frequency. So alpha is your 8 to 12, and beta is your 12 to 24 or 25. Um, Also, you find that a lot of the oscillations are spatially distributed, and they're also associated with different brain states, whether your eyes are open or closed, whether you are awake or asleep, whether you're having a seizure, and so on. So here's an example of a person who has their eyes closed and they open their eyes and then they close their eyes, and you can see that the magnitude of this wave is actually being suppressed when the eyes open, and it comes back when the eyes close. So that is because a lot of energy is going into the eyes and the perception of what the eyes are seeing. So the activity is shifted to another frequency band and also probably to another physical location. I don't know where this measurement was taken, but that would not be a bad assumption to make. Um, there is a band referred to as gamma. That is an upper band that tends to be like above 30 hertz. Most people take that as being 25 to 50 or 30 to 50, just depending on where you define your upper limit of beta. So people talk a lot about activity in these frequency bands, because it's one of the features or characteristics of the EEG that allows you to diagnose disease states. For example, we know in babies we see a lot of delta activity. In adults, a lot of delta activity is uncommon, and so that might indicate the presence of Alzheimer's disease or some other disease state. So that's what that is. Now let's go and look. Here are some abnormal EEG activity. This is a petit mal seizure. This is a grand mal epileptic seizure, and this is what's referred to as a psychomotor seizure. Um, Notice that within all of these, that sort of random nature, so we'll go back. Here's kind of a, if we look just at this portion of eyes closed EEG, you see there's a random kind of appearance that almost looks like noise. I can probably show you some better data than that. If you look here, you see a little bit more of a regularity and a little bit more, especially up here in this petit mal seizure, you see it almost looks like two superimposed sinusoids or a sinusoid superimposed with spikes. Um, this is very characteristic of an abnormal brain state. So when you see these spikes, as well as this almost really regular sinusoidal rhythm, that's a bad sign. That means that the brain is either in seizure activity or it's got some other abnormal state that it's entered. So that's just an example of kind of what different EEG patterns look like. You can also look at normal changes with normal things in humans. The top one here shows an excited state. So this would be maybe a person's watching a scary movie. Here is relaxed. People have done a lot of research recently into the brains of Buddhist monks who meditate a lot. You tend to see this waveform appear in people who are trained meditators. Um, and so you see more activity in certain frequency bands of those whose brains have been trained to meditate both in meditation and outside of meditation. Here is a person who is drowsy, and then here is a person who has fallen asleep. And so you see these isolated little areas of what are referred to as spindles, um, with more kind of chaotic activity in between. And then in deep sleep, you notice that these little spindles go away and the rhythm slows, and you can see that there's a very different characteristic between a deep sleep and just being asleep. Interestingly enough, there's also quite a different characteristic of being under anesthesia. So one of the ways that surgeons monitor now whether a person is under anesthesia is to look at the temporal nature of the EEG and determine when that level of anesthesia is reached. So this is just kind of a basic introduction to sort of the brain and how the EEG signal is created. There is a PDF file that has been included in your reading list that goes a little more into detail of the EEG and how the EEG is used to represent different brain states. There are a million things you can do with the EEG signal, and I won't begin to pretend that we can go into that now in this short lecture. Just mostly what I want you to get out of the lecture on EEG as well as the lecture on ECG and EMG is that when we look at these biopotentials, they arise due to electrical activity within the body. And typically, the measurement that we make is not a measurement on a specific cell or of a specific action potential. We're almost always measuring collective activity between groups of cells because that's all we really have the sensitivity to do when we do this outside of the body. So not only are we not measuring individual cells, we're also usually measuring the cells that we're interested in superimposed with some other activity going on in some other physical region. So what we actually get when we measure is a pretty convoluted, complicated picture of a source that consists of a number of neurons, usually the superposition of that source's electromagnetic field with others in the region. And so that would be considered, like a source of artifact because it's internal to the body, but it's not what you're actually trying to measure. So biopotentials and the origin of biopotentials and this whole thing within chapter 4 is a little bit more on the bio and a little bit less on the instrumentation, because it's important as you begin to make a measurement and interpret that measurement to understand what it is you're actually measuring. So this concludes the video lectures on the origin of biopotentials. There are sort of three things that a person needs to consider when thinking about measuring a biopotential. One is the origin of the biopotential itself. The other is the interface between the body and the instrumentation system. In other words, how do you design an electrode that actually picks up this voltage or current? And then finally, the instrumentation system itself, how we acquire and then process the signal. So the next step will be to discuss in chapter 5 a little bit about what happens when you put an electrode in contact with